Good. Okay. So I just want to say a few words because I think we're officially opening the spring semester with a seminar, and I'm delighted to have my colleague Paulo Dodorico here. And I've known Paulo for quite a long time. He's done some remarkable contributions to fields of hydrology, and hydrology as it connects to other sciences. Safa is going to do a little bit more of a formal introduction, but I wanted to have the privilege of saying some words. And last time, we're just reminiscing about last time we met, Paulo and I were actually stuck somewhere in the Everglades among alligators in an airboat that wasn't working. It was quite a fun experience. So it's a delight to have you here, Paulo, and essic is always your house. So I'll leave it to you, Safa, to get informally introduced, and we'll go from there.
Thank you so much, Fernando. Hello and welcome to the academic year. It's my real honor to introduce Professor Paulo Dodorico from University of California at Berkeley to start to kick off the seminar series at essic. Dr. Dodorico received his bachelor's, master's, and PhD from University of Padua in Italy. He was a student of the famous hydrologist Andrea Rinaldo, and since then he's been working in hydrology and ecohydrology, theoretical ecology, working on nonlinear sciences, and most recently on water and food security. Dr. Dodorico has published a large number of papers, over 250 peer-reviewed publications, and multiple books. He's been at UVA, University of Virginia, for more than a decade, and recently, about 2 years ago, he's moved to UC Berkeley and is now at the Department of Environmental Science and Policy and Management at UC Berkeley. So Dr. Dodorico has received numerous awards. If I want to list everything, it would take the whole hour, but most recently, he's been elected as a fellow of AGU, and he has received, he gave the Witherspoon lecture at EAGU in 2016, and also he's been a fellow of the Guggenheim Foundation, and he's received the top award of the Ecological Society of America in sustainability sciences. So with this, and without further details, I would just let Paulo start to talk. Thanks. Thanks very much.
Thank you. I think I have this one, but we need to. It's working. Okay, very good. Well, thank you very much for the invitation and for having me here today. It's an honor to be here in this institute. I'm going to talk about, this talk is mostly about water resources with respect to, and land with respect to the production of food and energy. And we will look at to what extent water resources can constrain the production of food and energy. If we look at the interactions of societies with the environment, many of these interactions are through the appropriation of natural resources, and water is one of them. And then if we look at the case of the pressure, human pressure on these water resources, we realize that the food is really the big player. So we will look at how the demand for water has been increasing over time, and we will look at these constraints, and then at mechanisms of redistribution of water resources through trade and international environments. And we will conclude with an analysis of implications for environment and society. So most of our water footprint is in agriculture, is due to agriculture, mostly in food production. And when people talk about a water crisis, it's a problem not of humanity that goes thirsty. That's a small number. Drinking water is just a small volume in comparison, but it's a problem of really feeding humanity. And so when we look at the use of water for agriculture, there are two different, I introduced some of the jargon as it became popular in the last 15 years. The part of the agriculture is rain-fed, and it uses only rainwater that infiltrates in the root zone and then is taken up from the soil by plants. This water is usually called the green water. It's not really accessible by humans, but is extracted by plants, because it's not available for gravity drainage. While in part of the agriculture uses also another type of water. It's defined blue water. It's the water that is taken from water bodies and aquifers and applied through irrigation. This has been going on since the antiquity to increase the agricultural production. Right now, about 20% of the land is irrigated. It produces 40% of the food. And then we can think that this food production has two types of footprints: water footprints, a green water footprint for the part that is contributed by the rain-fed portion of the production, and then the irrigation contributes to the blue water footprint. So if we look at the total amount of water used for irrigation, I like to compare this with the fluxes in the water cycle. You see that this number that doesn't tell us much unless we refer it to the volumes of water and the fluxes of water in the water cycle. Basically, we have agriculture claims 10% of the precipitation over land and 60% of the terrestrial evapotranspiration, which is a big amount of water if you think that not all land is suitable for agriculture. Irrigation is just about 10% of the water used in agriculture. So I said that this demand for water is increasing. There are three main factors: population growth, and then the increase in consumption of animal-based products, and then finally the production of other commodities that agricultural commodities that are not for food and biofuels are the production of biofuels has become pretty important in the last 10 years. So we can look at these separately. If we look at population growth, what is interesting to see in these patterns of population, in this trajectory of population growth, is that it took the whole history of humanity until the early 1800s to reach 1 billion, and then a little bit more than 100 years to reach the second billion. This is the time of the Industrial Revolution. And then it took 33 years to add another billion people on Earth. And this is often in the literature related to the Green Revolution, and particularly the Haber-Bosch process, the ability to produce nitrogen fertilizers that increased in a very unprecedented way the ability of humanity to produce food. And this led often to the perception during the Green Revolution that there would have been no limit to the ability to produce food. But then we reached, in the last 10 years, some new global food crisis. And the fact is that if nitrogen is not limited, there are other limiting factors, and water is for sure one of them. And then in addition to that, there is also the variability of climate and disturbances like wildfire, etc., that can cause disruptions to the system. And so the question often is whether the water resources may constrain the production of food. If we look at instead the changes in per capita food consumption, the big player here is the increasing reliance on animal products. And so this is usually known as Bennett's law, the idea that as income per capita increases on average, there is an increase in meat consumption. This is a snapshot for 2013 showing all countries, some of the main countries in the world. And this instead shows the trajectory of economic development of some big countries in the world. We see that clearly there has been an increase in the consumption of meat and general animal-based products. It takes on average between 4 to 8 times more water to produce 1 calorie of animal food than 1 calorie of plant food. And so clearly this change in diet has an implication also on our pressure on the global water resources. We have estimated in this study that we expect a 20% increase in the per capita consumption and the per capita water footprint as a result of this dietary transition. And The other thing that I wanted to show is that there is also an increasing, also the energy sector requires water. And so we can already mention the case of biofuels, and if you look only at bioethanol and biodiesel, which are commonly used for vehicles, their water resources are already 10 times more than the water resources used for the extraction of fossil fuels, and this is already a pretty generous estimate. So this shows that already the biofuels that meet only 2–3% of the energy demand for the transport sector are already using quite a bit of water resources. Then also non-fuel-based renewable energies require water. And typical example is the case of solar panels. So many installations are in arid environments where there is a lot of blowing dust and they need to clean and wash these solar panels. So if we look at biofuels, we see that there has been a clear increasing trend in the last few years. And then the policies behind that have been at the center of many debates. Up to the early this year when the European Union started to put a cap on the use of some of these biofuels. But what we find is that these would be the major crops. We use much more water for bioethanol because we consume globally much more bioethanol than biodiesel. In the USA, it's mostly corn. In Brazil, it's mostly sugarcane. And then for the biodiesel, this gives you the split among the different crops, but all of them have their own water footprint. And again, based on data for I think it was 2010, was only 2–3% of the water used in agriculture. Now it's a little bit more. If we look at the use of energy for the extraction of fossil fuels, the numbers are smaller. Before I was showing was of the ordinary of 10 to, depends on how you calculate them, but basically this is a small number. But the water footprint of fossil fuels is often calculated in terms of energy, water used for the extraction. But we don't consider the fact that we are using these fossil fuels were back in time were plant biomass, and it took some water to grow that biomass. So this calculation of the water footprint of fossil fuels is often incomplete. If we try to, it's very hard to know how much water was needed millennia ago to produce that fossil fuel. The only thing we can do is to use a replacement game and to replace natural gas with ethanol or crude oil with diesel, etc. And if we do this type of exercise and using present climate conditions, we see that the annual energy requirement would need about 73 to 10 to the 12 meter cubes per year. The number doesn't tell us anything, but it's very much comparable to the total terrestrial evapotranspiration. This tells us one thing, that by using fossil fuels, we are using water from the past. We call that ancient water, and that the water cycle will not be able to allow us to meet our current energy needs. So this again brings back the point that it's impossible to think to replace fossil fuels with biofuels because the natural resources, I'm looking at water, if we look at land it's even worse. So the only thing is that we need to look at non-renewable fossil fuels or look at non-fuel-based renewable energies. So the new trend is that now is that there is some expectation that by 2040, about 20%, there will be a 20% increase in fossil fuel use, and there will be an increasing reliance on unconventional fossil fuels. So this includes oil sands, tar sands, what is happening in Alberta in Canada, and then fracking of shale formations. The extraction of these fossil fuels requires much more water than the conventional fossil fuels. And we will see that in a moment. If we look at the global distribution of shale deposits in the world, we see that many of them are in regions that are water scarce. If we just look at North Africa or continental China, So where there aren't enough water resources to extract these fossil fuels, unless we where the extraction of these fossil fuels would enter in competition with water uses for agriculture. And so we have done an analysis in this study, and we saw that 31 to 44% of shale deposits are in water-stressed areas, and many of them are in areas affected by the depletion of 20% in areas affected by groundwater depletion. This shows us that it's really a short blanket, and then we are dealing with a situation in which water resources might be limiting. So the question is whether we are running out of water resources, and this goes back every time to Malthus and the theory of demographic growth being faster than the rate of availability of natural resources to feed humanity. This theory was disproved, or was a little bit put in a corner during at the time the decades of the Green Revolution, with a perception that of this unlimited growth and ability to produce food. Technological innovations, according to Boisrop, would allow for to expand the ability to produce food. And in a similar way, Sen, in the theory on famine and poverty, argued that there is no evidence of any natural resource constraining population growth on a global scale. And anyway, in the last few years in the environmental science literature, we have been alarmed many times about the fact that if we look at the population growth and the need to feed the human population by the end of the century, the agricultural resources might have been limited. And so, in an interesting study, more than 10 years ago, Folkeman, Ken Rockstrom calculated the amount of water needed to feed humanity at that time. And at the time, the population was 6.5 billion people. By 2050, we expect to have 3 billion people more. If we want to eradicate malnourishment, we need to almost double the water use for food production. And they argue that it would be possible to find this water partly by increasing irrigation, partly by through soil water management. And the idea here is that in the evaporative losses of water, evaporation doesn't do anything good because it's a very unproductive loss of water, while transpiration is coupled with photosynthesis. And so we need to develop some techniques that reduce soil evaporation and evaporative losses in a way that we can save water. And the other approach would be with the more crop per drop approaches, with the development of technologies, and including also new cultivars that have a higher water use efficiency. The idea of increasing irrigation is often found in many studies that tend to argue that agricultural intensification is the way to go, because the alternative is the extensification of agriculture, to expand agriculture on land that is not presently used for agriculture, which entails deforestation, losses of other natural habitats, and losses of biodiversity, and also an increase in CO2 emissions. Or other people could argue that we might have to do both things, but the problem we have with irrigation, agricultural intensification, is that one way to increase yields is to increase irrigation. And many times when we look at the global distribution of the yield gaps around the world, we don't account for the fact that to close the yield gaps in some regions, there might not be enough water resources to do that. So there has been, again, a new trend in the last 10 years in the literature. Some scientists advocating for the sustainable intensification, so some ways to intensify production in a more sustainable way without depleting groundwater, without using natural resources, again, and depleting natural resources. We did this study here to look at to what extent it's possible to sustainably close the yield gap without again, depleting water resources. So the blue and the red color, this paper is still in review, hopefully will be accepted soon, but in blue is where irrigation is performed now in a sustainable way. And then in red is where it's done in an unsustainable way, in the sense that we remove blue water flows, so basically groundwater and surface water in an unsustainable way, which means either depleting groundwater or using environmental flows. And then in blue, in green and yellow, you see regions of the world where it's possible to expand agriculture, expand irrigation on rain-fed areas. So these are regions where that are still used for agriculture, but where we can close the yield gap by bringing irrigation there. And in some regions, you see, it's not possible to do that in a sustainable way, again, without depleting environmental flows or groundwater. So if we account for that, well, if you look at yield gaps, we would be able to feed 4 billion people with the present diet. If we do these calculations, we look at the sustainability requirement, we see that it's possible to feed 2.8 billion people. Still, it's possible to feed humanity looking at these long-term scenarios, but not all regions of the world are suitable for this intensification of agriculture. And so, what is interesting is that this allows us to increase the production of food and increases also, again, the use of water resources, but without using more land. So in general, when we look at this intensification of agriculture, ecologists tend to be very excited about that because there is no habitat loss, but there are some impacts on human societies, and mainly the fact that in regions of the world where the yield gap has remained open, there are many of these regions are in the developing world where there have not been investments in new technology because of lack of capacity to make those investments. Can be financial or also institutional capacity. And so when we look at the major innovations that have increased the ability to produce food, of course we started with we already talked about the Industrial Revolution. Just think about the ability to pump water from aquifers and or build irrigation canals, etc. The Green Revolution, we have had a great impact in the ability to increase production. There have been other revolutions in the last 2 decades that we are going to talk about now, and these are framed here. We will talk about this, can define it, trade revolution, since we are, seems to be a very revolutionary field. But so this, the increase of connectiveness in the trade and reliance on food produced in other parts of the world. Then we will talk about the closure of the yield gap and how sometimes these investments that have been lacking in the developing world in the last 10 years have been happening through large-scale land acquisitions, often called also land grabbing, so in a sense that foreign or also domestic investors have been displacing subsistence farming and promoting large-scale commercial agriculture. From the point of view of food production, clearly there is an increase in food production, but this has an impact on rural livelihoods, and we will briefly talk about that. We define this as the fourth food revolution, and then the next step, there could be some sort of way to look at the future is whether there are opportunities to do this intensification in a sustainable way, both with respect to the environment and rural livelihoods. When we look at, let's start with the trade now. If we look at areas of the water resources compared to the population of some countries, it depends on how you may do these calculations, but there are some areas that there is an abundance and areas where there is a scarcity. And then without focusing too much on the specific country, conceptually we have a situation in which if the demand exceeds the supply, we have a water deficit, and we can avoid this deficit in two ways, either by reducing consumption, which means reducing waste, but also accepting some undernutrition levels, or by importing food from somewhere else around the world. Then this means, and of course the ability to produce food is controlled by climate and natural resources, that somewhere else around the world there is an excess of resources, there is a surplus, and the ability so to establish a trade of commodities, and by trading those commodities we are trading also what is defined virtual water. Virtual water is the water required to produce the commodity. The notion comes from Alan, who realized that the North Africa and the Middle East had the population exceeding the local water resources. There were no water wars, and the reason why this was not happening is because there was a strong reliance on import of grains from North America. In fact, the virtual water flowing from the US to that region exceeds the physical water flows down the Nile River. So, and since then, there has been an exercise in calculating this water footprint of different commodities. What our group has done has been to quantify these fluxes over time and to see how much virtual water trade has been changing over time. So when we talk about trade revolution, we refer to the fact that unfortunately this data of bilateral trade of commodities are available only after, at the global scale after 1986. In this time period, there has been a tremendous, a great increase in the amount of virtual water trade, and we have reached this number of 2.8 10 to the 12. So if you look at geographically the distribution, we see that these arrows are proportional to the fluxes, and only the main arrows have been plotted here. There's been a big increase in virtual water flows. One thing that we notice is not only increase in volumes, and also increase in interconnectedness in the world. The world has become more interconnected. South America has become more integrated and more plays a protagonist role in virtual water trade. Look at the flux from Brazil to China. This is something that didn't exist in the 80s or was much weaker. And if we look now at the main net exporters, we have that 4 or 5 countries contribute to more than 50% of the net virtual water exports. The US used to be the main one, now is number 2, Brazil, Argentina, and I think the third one is Indonesia. So this means that we always think about the concentration of power associated with the concentration of oil, for example, in a limited number of countries. But there is also a strong reliance on water resources that many countries don't control because they are present in the other part of the world. I think these are the main comments. Then you can see that we can see a few the same results. We've done an analysis using a different currency, now calories instead of virtual water. Same story, clearly, because they are still the same price fluxes. But the general message is that 24% of the food and 24% of the water, virtual water we use with that food is traded, and we have access to these resources through international trade. So interesting also to look at the interconnectedness. This is the number of connections over time. The world has increased globally the number of connections, and Africa is still more marginally involved in this global trade. We see more red or orange and less green, which means basically there is, while Southeast Asia over time has become more integrated in the global trade, Africa is a little bit less than that. So let's compare these fluxes with since we are earth scientists, we like to compare with the physical fluxes of water. And again, here in this figure, I try to put together the different values. What is interesting is that the physical fluxes remain the same. Global evapotranspiration remains the same over time, but what changes is trade has been increasing over time, which means that water is the virtual water trade is becoming a bigger and bigger component in this system, and so these fluxes have been becoming a bigger fraction of the total terrestrial evapotranspiration. I said 16% of the evapotranspiration is due to agroecosystems, and 1/5 or 1/4 of that is traded. And so similarly, we can see also feed is a big player in this trade. So many of these plants or crops that are traded are, for example, soybeans or other crops that are used for feed. And we can use the change currency, switch to land, and we see that the land area you traded, virtually traded with the feed, has become 3 times bigger in the course of this period. So what are the virtues of virtual water trade? So one of them is really that we avoid famines, we avoid mass migrations, we allow people to have their food without having to relocate themselves. And so this is definitely a good result. Overall, there is a decrease in inequality, and there are also some water savings, we will see this at the end, associated with trade, in the sense that we tend to produce commodities in areas where their water footprint is smaller. Here, if we look at the inequality, which is usually calculated with this Gini coefficient, which is variable between 0 and 1, we see that naturally inequality is much bigger than the inequality in the actual inequality in the production of food locally, or in the access to food through trade. So trade overall reduces the inequality between those who have and those who have not enough resources, which explains the fact that we have regions like North Africa or the Middle East that don't have enough resources to feed themselves, but the trade brings this food in these regions. The negative aspect is that it creates some trade dependencies. So there is a loss of resilience if there is a dependence on resources that a group or a community or a country cannot control. There is also a loss of ecosystem stewardship because we tend to care more about the environment that is in our backyard and not what happens on the other side of the world. So the production of soy in Brazil is having impact on land use change and pollution that are not going to affect directly the consumers on the other side of the world, who indirectly are driving this land use change. Then it's not a long term to the solution of a food crisis, because as the demand keeps increasing, we are just redistributing what we can, but in the long run, we might still run out of resources. And so overall, the trade dependency is really a concern, disturbing, because there have already been examples of situations in which, in conditions of crisis, trade-dependent countries have been have remained with more limited resources. So we have done some studies. It's very hard to study the resilience of this system, mainly because the economic models, trade models, tend to be equilibrium models. And if you have a shock, this shock is not, the system is going to be not in equilibrium. And so the only thing we can do, and this is just a very simplified approach, we need to conserve mass. We know that, and there is evidence of the fact that the countries tend to use their reserves when they are in conditions of crisis. They tend to reduce their exports and to increase their imports. So if we take the case of Argentina, for example, we could think that if there is a shock in production shock in Argentina, this shock, Argentina would first reduce the exports, increase the imports, and use its own stocks. And we can see how this propagates around the world. And of course, this is based on very simplified rules and nothing fancy. But based on the existing trade dependency and trade partnerships of Argentina, you see that something affects one part of the world can have a global impact, which is not a big surprise. So we have done other studies try to quantify the stability of the system. So if we think of a set of differential equations representing the population growth in each country, depending on the carrying capacity, so on the resources existing both locally and through trade, we obtain an interconnected system for which we can study the stability of the trajectory of growth, using the Lyapunov exponent or using other indicators of reactivity of this system, because if a system is stable, it can be stable asymptotic in this way, but it can still be at the beginning of the perturbation, respond first with an increase of the perturbation and then a decrease over time. This increase in perturbation is interpreted as an indicator of a transition, of a critical transition to an instability. So with this approach, it's possible to study some of these property of stability and resilience of the system, and even identify areas that are more vulnerable, and not surprisingly are areas that are also affected strongly food dependent, trade dependent. Another thing is that trade is not a long-term solution, because again, if you take a look at what happened in some of the recent food crises, we see that in condition of crisis, of production crisis, being trade dependent is really a weakness. We tried to study this by looking again at trajectory of population growth, using a logistic growth with, again, a carrying capacity that depends both on local resources and global resources that are accessed through trade. And then if we just look at the data, we see that there is a general pattern here, that countries that are resource rich and are net exporters, they tend clearly, if we fit the logistic growth, we see that in their long-term trajectory of population growth tends to follow a trajectory that is driven only by local resources without accounting for the fact that some of these resources are exported. Instead, if we take some of these trade-dependent countries, we see that necessarily their trajectory of population growth follows, again, a trajectory that is based on global water resources, so depending also on imports. So what this analysis shows, and I can show this for many countries around the world, it's in this paper, in the appendix we put this information. We see that the long term, while net importers rely in their trajectory of demographic growth on food imports and also virtual water imports, the net exporters still count for their long-term trajectory of population growth on their local resources, without accounting for the fact that part of them are presently exported. So this means that there are two groups of population that are relying for their long-term growth on the same pool of resources. So what happened in the food crisis of 2008 and 2011 is that net exporters, because of the escalation of food prices, their governments banned exports or reduced exports. And this caused a condition of panic in net importing countries, particularly in countries that are not particularly affluent, and for which, and for these countries, paying the food a higher price became a problem. A almost tragic example was the case of Nauru Island, which is often used in classes to talk about a paradigm on sustainable use of resources. They had to their food prices were high because they're imported, and there were big costs also of transportation, and they were really having a hard time facing this crisis. So this is just to say that this is not a long-term solution. At some point to trade, we redistribute resources around the world, but this is again a short blanket, and if there is a crisis, whoever controls the resources will use them first. This could be a general thing. And so this is, again, the crisis of 2008 was partly caused by some extreme events, by decreasing reliance on biofuels. And then what was found is that there were export bans, and there was a condition of food insecurity. This led to one thing, that awareness about the possible emergence of new food crisis, and awareness of the fact that there are still regions of the world, as I said before, where there are big yield gaps. And this motivated the interest of some corporations, agribusiness corporations and countries and national governments also to get a more direct control over those resources. And also in part with the justification that by bringing new investments it would be possible to close these yield gaps. This has led to large scale land acquisitions, which has been a phenomenon that we heard a lot about in the news. And years ago we tried, this is completely outdated because this was 2013 we did this study, and we reconstructed the global patterns of investments, which can be also criticized because many times the investor is can be not only an individual, but can be a corporation that, or can be a joint venture among different countries, including also the target country. But in terms of area, this is a big area. It's 4 times the area of Portugal. It's greater than the agricultural area of Germany, and is greater than the area of Italy, which is the most important reference point. So this gives us an idea of how of the magnitude of this phenomenon, and the justification is often been to intensify that in this way it's possible to close the yield gap, so to intensify production. Then the counter argument has been then, well, by intensifying production, we displace local farmers. And then many other times in the literature we find that the new investments are not in existing agricultural land, but to develop virgin land. So it becomes a problem of extensification of agriculture with other concerns about land use change and deforestation. So we try to answer the question of how much more food can be produced and what is the role of water. I'm going to show here results only for Africa. You see that there is, it's possible in Africa there are big yield gaps. It's the difference between the black and the white bars. And so it's possible to increase a lot, by quite a bit, the production of food and really produce enough food to feed the malnourished population of Africa. And the reality is, however, is that the food is often produced for the export markets, and that in many cases the land is acquired, but it's not put under production right away. So even the arguments in favor of foreign direct investments, that are the arguments of the trickle down, the fact that by bringing new investments you bring more jobs, more employment, education, access to markets, etc., cannot happen when this land is just acquired as some sort of option for the future, but not developed, and excluding also local population for the use of this land. So we associated with this acquisition of land, there is also an acquisition of water, because many times the investor country can be in a water-limited region of the world, like countries in the Arabian Peninsula, or and these countries invest in Sudan or in Ethiopia along the banks of the Nile River just because of the presence of water. So we quantify the amount of water that can be acquired through this process, and probably for us, and we try to see both in terms of blue and green water. If we look in terms of amounts, it's not a negligible amount, because if we compare to virtual water trade, for example. We tend to often to refer to groundwater depletion as a form of grabbing of water from the next generation, and its magnitude is less than the appropriation of water from our neighbors or far neighbors. I mentioned also the concerns about deforestation, land degradation, and land use change. We see that many of the areas, the forested areas, many of these land investments are in hotspots of deforestation. Typical example is the Kalimantan, where there have been land concessions for oil palm production, and you see that these concessions are also where you find most of the tree cover loss. We did a similar study here in Cambodia. In Cambodia, they call them economical land concessions. It would be the red polygons, and you see. And then we quantified the forest loss within concessions in non-concession areas, and with the non-concession areas are used as a reference point, and we use only areas that had similar physical properties in terms of distance to roads, water courses, etc., and population density, in a way that was a fair comparison. And again, these land concessions are hotspots of deforestation. So we tend to, another thing we tried to do in respect to these land investments, we tried to look whether the favorite target of land investors were land areas where there are non-well-defined property rights, so the so-called fuzzy property rights, or common property regimes. We found that the commons are a preferential target of the land investments, and we define this phenomenon as the tragedy of the grabbed commons. For those of you who are familiar with the literature on the commons, there has been, in the 80s, the argument that the commons, since they don't belong to anybody, they are poorly managed, hence the tragedy of the commons. And then Ostrom, a Nobel Prize for Economics, realized that this is not true, that the commons have local institutions and traditions of good management due to the way the community organizes itself, and which makes the commons particularly resilient, and more resilient than even than private property regimes, because since the land doesn't belong to anybody, nobody can sell this land, and the land remains with the community as a source of livelihood. While it's true that the commons are very resilient with respect to endogenous forcing, they appear to be particularly fragile with respect to this exogenous forcing of the land investment. And so when earlier I mentioned these different options, and we went through these mechanisms of intensification through irrigation development and also through these large-scale investments. And then we said that extensification has also some problems, and we saw that also land acquisitions lead to some of this extensification. And I refer to this sustainable intensification as a way to intensify production in a sustainable way, so without depleting groundwater, without losing rural livelihoods. One of the ways we proposed in this paper is through a more efficient distribution of crops. So in this study, we just look at areas that are presently cultivated. If it's irrigated, we keep irrigation. If it's not irrigated, we don't even introduce additional irrigation. But what we are doing is that we select the crops that allow us to increase production. And this is done on pixels. I think it was 10 by 10 or 50 by 50 kilometers. And within these pixels, we don't want to decrease the number of crops because we don't want to lose, again, diversity of crops, which can give resilience to this system. We just replace crops in a way that we increase the production. Again, we don't want to deplete soils, so we don't replace pulses or nitrogen fixers with crops that are not nitrogen fixers. And so even the protein production in the system is maintained. And so by doing this exercise, we find that it's possible to increase the production and feed 800 million people more, and to reduce the consumption of water. And so this can be a strategy for sustainable intensification, so increase production without requiring any new technology or any new particular investments, just to finding the right crop for the right place. Clearly, this is an ideal scenario. Of course, there are many other factors that come into play when we talk about the selection of crops. There are economic factors, there are also cultural factors, etc. But there is some degree of freedom to move in that direction. And the other authors have indicated other ways in which we can save water resources and produce more by using other methods. So this is our approach. I said that we can save this amount of water, which is a non-trivial amount of water, and cubic kilometers is 10 to the 9 meters, so it's a non-trivial amount of water. Then other ways is through improvements in crop water productivity, in irrigation, promoting irrigation efficiency. What I was talking before in terms of reducing evaporation. So we want, transpiration is a productive use of water, but evapotranspiration is unproductive. So with new agricultural techniques, mostly with mulching or with no-till agriculture, it's possible to save water. Then we can try to minimize food waste. This is based only on blue water, so irrigation water, but of course we save much more water if, in terms of green water. Waste presently is, according to this author, is 24% of our consumption is, or production is wasted. According to some other estimates, is even more than that. So there is a lot of saving that can be done here. Otherwise, the other way is to change diet, and other studies have tried to quantify how much water we can save by shifting to diets that have less reliance on meat. In terms of the reduction of food waste, we could advocate for even the food systems to use the approach, these paradigms of the circular economy. We have seen quite a bit of this in the literature in the last few years. But clearly, the model of production on which traditional agriculture is based is a linear model that uses resources to increase waste. And waste here is a physical waste of food and also pollution and in water courses, etc. Nature clearly works in a cycle. And the biogeochemical cycles have a closed loop, and by developing nitrogen fertilizers, we have opened this loop. So we have increased the production of fertilizers and increased pollution in the environment, and this has led to eutrophication, etc. So clearly, this is not a model that can sustain itself for a long time. So the idea of repurpose, you use some of these resources, can be a good way to save on resources, and we can think about way of doing this also with water and also with the fertilizers dissolved in it. When I started with this talk, I was referring to coupling between environment and society. What I try to see is that this coupling is, of course, often through these patterns of globalization, and then the main conclusions of this talk is that through these patterns of globalization associated with trade and international investments, there are some benefits, but there are also some big problems associated with the loss of resilience and loss of livelihoods. And so with this, I conclude this talk, and I'm sorry if I ran out of time. Yeah. Thank you.
Any questions?
Yeah, I was just wondering, is this on? Doesn't matter.
Yeah, it is.
Early, I don't even want to guess a slide number. You had something on yield gap kind of globally, or maybe it was even focusing on the United States. What jumped out to me was what's the yield gap based on? Was it like a specific crop or a basket of crops? And the reason that it jumped out to me was that we had North America having a significant yield gap. There was a lot of land area that was reported as having yield gap, even though I think of that as a place of very high yields, with the exception of a couple of crops like wheat.
Should we go maybe back to the slide? So
okay, it might be hard to find.
I think probably I didn't present that slide properly. It was an irrigation to close the yield gap, but I don't think it was a map of yield gaps. So this is why we go back. Do you refer to? Yeah, yield gap closure, right? Yeah, but this is. Is basically yield gap closure by increasing irrigation. So those are areas like those green dots where there is no irrigation, but where it would be possible to increase irrigation. But the part of the yield gap closure that is associated with fertilizers, for sure, we are, as you're saying. Yeah, exactly. Yeah, in that sense, yeah. But I agree with you. North America is a very small. Overall small yield gap with respect to use of fertilizers or other inputs. Yeah.
Thank you very much for the very fascinating talk. A lot of good work. It was very interesting. My question: I've noticed that a lot of the analysis you're showing were more historical in nature, and I was wondering if your team you're doing any modeling where you look further into the future. Some of the work we do here that we're involved in, we look at projection of how the human system might be evolving, looking at let's say the Paris Agreement and how different nations are trying to meet their targets and how those might affect some of the analysis you're doing. I was wondering if you can comment on whether that's something you guys are engaged in or interested in. Thank you.
Yeah, thanks. This is a great question. So as you have seen, what we have done is mostly looking at the past, at the recent past and trends from the recent past. We haven't done much of projections in the future in terms of climate change or so that would be something I would be very interested in.
We should talk.
Yeah, sure. Okay.
Other questions? I use my prerogative as the host to ask the last question. So how do you see this research going into tying into coupling the population and the human system with the dynamics of human population growth, with water availability, food availability, and and the whole the evolution of the whole system?
In the model, you mean?
Modeling.
I think it requires getting to more, we try to do something more on the demographic component, but there are things, other aspects that are related to, again, the dietary shifts and other types of consumer choices, yeah, which are more complex. In addition to that, even the trade patterns, which are, again, part of, are very hard to model or to predict how it will change over time. And these are things we haven't worked much on, but are clearly interesting. Also, the part of the demographic growth models cannot be only driven by the factor of by water, but there are many other factors going into that. Those were here studied just mostly to see whether we have any evidence of possible constraints from water resources, but clearly the demographic modeling is much more complex than that.
Thank you. Okay, so let's thank our speaker again for the excellent presentation. Thank you.
Thanks. I didn't realize we were going. We did it.